Another common oscillator that we're going to talk about, and I've mentioned before, is a pendulum. Now, technically, there's two types of pendulums we're going to talk about. One is a simple pendulum. A simple pendulum is defined as one that's essentially a string that has negligible mass, and all of the mass of the pendulum is located at the very end. So the mass is concentrated at the end, some distance L from the pivot point. So the pivot point is up here. As we pull the mass to the side and release it, it's going to start swinging back and forth. The other type of pendulum is called a physical pendulum. That one, essentially, the mass just is not concentrated at the end. So it could be like a thin rod or a rod in general. If you've ever seen a grandfather clock, they often have a big thin rod and then some sort of disc at the bottom, and they swing back and forth as well. So ultimately, the difference between the simple pendulum and the physical pendulum is whether or not the mass, where the mass is. So for a simple pendulum, the mass is concentrated at the end. The string that connects the pivot to the mass is negligible in mass. A physical pendulum, the mass is not concentrated at the end. It's distributed somehow along the length. That's ultimately the difference. In either case, it's the force of gravity that is causing the swinging of the pendulum. We know the force of gravity is acting straight downwards. It has a component that points directly towards the center and a component that points tangent to the motion. And it's this component that's tangent to the motion that is directly involved in the oscillations. So if we talk about our angle in here, let me draw an angle. The angle that the pendulum makes with the vertical, we could draw it down here as well, which means it can be drawn down here. So if we were to draw these components of gravity, remember they have to meet at a right angle, this component here would be mg sine theta. That is the force, the net force that is tangent to the motion. This is the force that's causing the acceleration in terms of causing the pendulum to speed up or slow down. And so we can say that mg sine theta has to equal the mass times the acceleration. The mass cancels. So the acceleration of the pendulum is going to equal g sine theta. And theta, of course, A is g sine theta. Now this is in terms of magnitude. The direction is going to depend upon where in the motion we're talking about. So it turns out, since A is the second derivative of some sort of position, essentially the angle with respect to time, we get a differential equation again where theta, the angle that the pendulum makes with vertical, is changing with time. Now, our author walks through this solution in the e-text if you'd like to walk through it and see it. There is an assumption made, and it's a small angle approximation. So this is valid for angles less than about 10 degrees. Now, theta max would be the maximum angle in here that we pulled the pendulum to the side and then released from rest and allowed it to oscillate. If we use this equation, theta must be in radians because of the small angle approximation in the derivation. Ultimately, though, if we were to take the derivative, pass it back through our equation, we find for a simple pendulum, omega, the rate at which it will oscillate, is the square root of g over L. So g being the acceleration due to gravity, so the free fall acceleration, and L being the length of that string that is holding up to the mass. We know omega is 2 pi over f, or 2 pi over t. So we could write the period of a simple pendulum as 2 pi times the square root of L over g. So the rate at which a simple pendulum is going to oscillate depends upon how long the string is, and it depends upon the acceleration of gravity. The solution for a physical pendulum is similar, but it looks like this. So m, the mass of the pendulum as a whole, g, acceleration due to gravity. L in this equation is not the entire length. It is the distance from the pivot to the center of mass of the pendulum overall. So the center of mass, if I come back to the picture I've drawn over here, center of mass is going to be somewhere shifted from the center of the rod towards the disc at the end. L in this picture would be right here. So from the pivot at the top where it's connected down to that center of mass. I is the moment of inertia, also called rotational inertia. We talked about this back in rotation. So first semester of physics, when we talked about like net torque is I alpha, the rotational kinetic energy, 1/2 I omega squared. The moment of inertia talks about and relates to how easy or hard it may be to change the rotation of an object. The larger I is, the more torque, the more energy needed to change the rotation of the object. And I, in turn, comes into play in the angular frequency. We could write the period of a physical pendulum using these same relationships of omega is 2 pi f or 2 pi over t. That's a general relationship. We would get I over mgl. Now, one thing to think of is that m is going to cancel. If we plug in the equation that describes I always related to some sort of coefficient and then a mass and some sort of distance squared. So the mass still cancels out. The mass is not going to determine period. Now, if you refer back Right now we're using the Knight 5th edition. If you refer back to that, you can find the table for I. So I've pulled the table from our book, our current author. We had this table of moments of inertia. So depending upon the shape of our object and how the mass is distributed relative to the rotation axis. So remember, these lines in here represent the rotation axis, which is where the pivot is. We can calculate the moment of inertia. If this table does not include what we have, so for example, the picture I drew, maybe we had the thin rod and the disc, I can find I total by taking I of the rod itself plus I of the disc at the end. The total I for a system is equal to I of the individual objects. Here, since the pivot's at the top, I would choose the thin rod about the end, so 1/3 ml squared, where L is the total length. And then I would also need to add the disc. But the disc, in terms of our picture here, this gives us the rotation axis through the center. And this disc is not rotating through its center. And so we would need the parallel axis theorem. I knew, so I through this new axis. Here, I knew for the disc would be up at the end of that rod. I knew is always equal to the I that is valid for rotation around the center of mass, plus md squared. M is the mass, d is the distance from the new axis to the center of mass. So assuming the disc is attached at the end of the rod, such that the center of mass of the disc is at the end of the rod, I of the disc around this new axis would be, well, through the center is 1/2 mr squared, plus d would be L, the length of the rod. So the total I of this system, we would have 1/3 ml squared, where this m is the mass of the rod. So the 1/3 ml squared represents the rod itself. And then the disc, we had to use the parallel axis theorem because we shifted the axis. And so this would be the total I. If we then wanted to figure out omega, for example, we would have mgl over I. This I is what would go in here. The L, this L right here, would need to be, we would need to figure out where the center of mass is. It'd be the distance from where the center of mass for the system as a whole to where that pivot point is at the top. Okay? We're not going to give you anything too incredibly intensive in terms of figuring out L and I. If I was to give you a problem like this, I would tell you where the center of mass was at least, so that you would know L. But keep in mind, the L in this equation is not the length of the entire rod. So we do need to recognize what these different L's mean. Now, scrolling back up here, we have these general equations. These are specific to simple harmonic motion, meaning ideal oscillations. So a simple pendulum, omega ends up being the square root of g over L. In this case, L is the total length of the string because, again, a simple pendulum, the mass is concentrated at the end. So the distance from the pivot to the center of mass is the entire length. A physical pendulum, omega is the square root of mgl over I. In terms of energy, when we talked about a mass spring system, we talked about energy as well. Since we're still talking ideal situations, the total mechanical energy is constant, meaning potential energy and kinetic energy are just changing back and forth and back and forth. There will be moments in time where the energy is all potential. So mgy max, the highest it swings. So we're talking gravitational potential energy here, and that's why we're using mgy. There will be moments in time where the kinetic energy is all we have. And that would be as the mass swings through its equilibrium location. And by equilibrium, we mean if the system was at rest, where would it be? Well, it would be hanging straight downwards. So as a pendulum swings through its lowest point, this is where it will be moving fastest. Everywhere in between, it will have some potential energy and some kinetic energy. Okay. Now, just quickly, you're going to see on the test notes, at least as for now, mgl times 1 minus cosine theta max. Where this comes from is if we draw, let me scroll up just a little bit. If I draw my pendulum at its maximum height, y max, that means in equilibrium, the pendulum ball, the mass would be at the bottom. L in that, capital L is what they're using, represents the length of this string. Theta max represents the maximum angle that the pendulum swings to, which is why this is a y max. That's the highest it goes. Well, y max is simply this height right here. The total length is this L. So y max ends up being L minus whatever this portion is. And just using trig, if I think about the triangle I have on top, this side's L, this is theta, this side would be L cosine theta. So if I take the entire length and subtract off L cosine theta max, that is my y max. And so when we write out mgy max, we get mgl minus mgl cosine theta max. They've factored out the mgl portion, and then we have 1 minus cosine theta max. That represents the maximum potential energy, which in turn, as the pendulum swings to the bottom, will turn into kinetic energy completely, and then everywhere in between would be potential plus kinetic. So we could just say y at any moment in time is L minus L cosine theta, where theta is whatever angle the pendulum is at that moment in time. So basic equations for pendulums. Again, we have two types of pendulums we're going to talk about, the single versus the simple pendulum versus the physical pendulum. And the difference is just where the mass is located. If the mass is at the end of a string, implying the string is negligible in mass, then that is simple. If the mass is somehow distributed throughout and not all at the end, then we have a physical pendulum. So I'll go through a few examples, and hopefully that will help as well.